Okay, so oxidation, reduction, reactions. We say oxidation reduction reactions involve two opposing yet complementary processes. What does that mean? Oxidation is the opposite of reduction. As opposing as these terms look, and the processes that they're opposing actually, but as opposing as they are, they complement each other. What does this mean? That there is no oxidation without reduction. That's to every oxidation, there must be a reduction. So equations where oxidation occurs, reduction will occur. And so if this happens, and when this happens, we say that's an oxidation reduction reaction. So we get to oxidation number. From our definition, we say oxidation number is the number of electrons an atom gains or loses to form a compound. So an atom will gain electron to become a compound, or it will lose electron to become a compound. Or you say it is the charge an atom would have if the compound is composed of ions. How do you know if a compound is composed of ions? When you see a positive sign on top, like we say H3O plus, that means it's an ion. It has a sign, a charge. Or we see a negative sign, SO2 minus. That's an ion. So the charge that atom has is the oxidation number. There are rules in calculating oxidation number. You have those rules in your notes, but I'm going to summarize it. In a way that will look simpler, will sound simpler. Okay, let's see. Element by itself has oxidation number of 0. An element standing alone, not combined with any other element, means it's by itself, it's standing alone. Like we say sodium standing alone, Na, the oxidation number is 0. So all elements standing by itself, oxidation number is 0. All group 1 elements have oxidation number of what? +1. Group 1 elements have oxidation number of +1. The same thing with group 2. Group 2 elements have oxidation number of +2. This always stands. Now, that does not stand for group 3, group 4, group 5, group 6. So it's only group 1 and group 2 that it can be always group 1 and 2 respectively. So all halogens usually have oxidation number of -1. But when it's bonding with oxygen, that's when an halogen is bonding with oxygen, the oxidation number is +1. What do we mean? You know halogens. You were taught halogens last time. Halogens like chlorine, bromine, iodine, and the rest. When they are bonding with other elements, the oxidation number of those halogens is always -1, except it's bonding with oxygen. When it bonds with oxygen, the oxidation number of that halogen becomes +1. Now, the oxidation number of a monoatomic ion is equal to the ion charge. What are we saying? A monoatomic ion like zinc 2 plus, Zn2 plus. So the 2 plus there is the overall ion charge. So the oxidation number of that element, Zn2 plus, is +2. The oxidation number of hydrogen is always +1 with non-metals and always -1 with metals. Oxidation number of oxygen is usually -2, always -2, except it is with peroxides. Peroxide is H2O2. So when oxygen is bonding with hydrogen, oxidation number of oxygen is no more -2, it becomes -1. So oxidation number of oxygen is always -2, except with peroxides where it is -1. Oxidation number of fluorine is always -1. Wherever you find fluorine bonding with another element, oxidation number of fluorine will always be -1. And the sum of oxidation numbers for a neutral compound is 0. A neutral compound is a compound that does not have a charge. So we can say SO2 minus. There is no minus, there is no plus, it's just SO2. That's a neutral compound. The oxidation number of such a compound is equal to 0. But the oxidation number of a polyatomic ion, a compound that has a charge, SO2 minus. Now, if it's only minus, that is 1 minus. it means the oxidation number of that compound is equal to -1. So the oxidation numbers of a polyatomic ion is equal to the ion charge. SO2 minus oxidation number of that compound is -1. So if you have 2 minus on top, the oxidation number is -2. If you have 3 minus at the top, oxidation number is -3. If you have 3 plus, oxidation number is +3, and the rest. Alright, so today we are going to deal with changes in oxidation numbers. Changes in oxidation numbers. Now, during the process of oxidation, a substance loses electrons. That's why I said that the third definition that is on electrons is the most important, because we're going to be using that a lot. During the process of oxidation, a substance loses electrons and its oxidation number increases. Take note, when a substance loses electron, what happens to the oxidation number? It increases. Okay, now in the oxidation of an ion atom, ion Fe, to ion 3 ion Fe3+. Now listen very carefully, because what I'm going to explain is not in your notes. Listen very carefully. The Fe atom loses 3 electrons, one at a time, to form the Fe3+ ion. Listen, therefore its oxidation number increases from 0 to +3, as shown in the equations below. You see the first oxidation state and the second. But that's not what I want you to listen really. Now listen, when an element loses electrons, electrons are negative. When an element loses electrons, they gain positive charges. What I mean is, think of it that you are an electron. If you lose negative things, you discover you become more positive, right? Good. To put it that way. So if you are gaining negative things, do you become more positive? No, you become more negative. So listen again to this statement. When an element loses electrons, they gain positive charges. So we can put it this way. When an element loses electrons, they become more positive. Now, the other way around. When an element gains electron, they gain negative charges. Do you understand? So it means when an element gains electrons, they become more negative. Remember, electrons are negatives. Just like if you gain negative, if you are attracting negative things to yourself, you become more negative. But if you are losing the negative things, throwing away the negative things, you see, you start becoming positive. You understand? So when you lose negative things, when you lose electrons which are negative, you become more positive. That's what happens to elements too. So, but if you are gaining negative things, you are gaining electrons which are negative, you become more negative. So take that statement down. When an element loses electrons, they become more positive. And when an element gains electrons, they become more negative. So if you have taken that down, you will see that equation. We'll read that statement again. The Fe atom. Now when it was Fe, you didn't see any positive sign on top of it. So it lost 3 electrons. Remember, when it loses electrons, it becomes more positive. So since it lost 3 electrons, what's the outcome? It became Fe3+. It has gained 3 positive charges because it lost 3 electrons. Do you understand? Good. So when that happens, we say the oxidation number of Fe has increased from 0. See, when it was Fe, remember, oxidation number of an element standing on its own by itself is 0. Fe there was by itself, no charge, no element by its side, so it's just Fe. Its oxidation number was 0. So the oxidation number increases from 0 to 3, since Fe3+ is now a monoatomic ion, an ion that has only one atom. The only one atom is Fe, ion. So the ion is 3+. So that's a monoatomic ion. We said the oxidation number of a monoatomic ion is its ion charge. The ion charge in that Fe3 plus is 3 plus, so the oxidation number is plus 3. So we can say the oxidation number of Fe increased from 0 to plus 3. Now, we said also in the oxidation number of iodine ion. Now, when you hear ion, it's not free, it has a charge. Now, you've not been told if it's 3 ions or 4 ions, you understand? If it's 3 plus, but when it's a iodine ion, it's expected that it's just 1 ion. So, iodine ion should be minus. You understand? Iodine. Since iodine is halogen, and we say oxidation number of halogen is always minus 1. So, iodine ion is minus 1. So, but when it's called iodine atom, it means it's not a charge. It's not an ion now. It doesn't have a charge. It's just standing alone. Like Fe was standing alone, but Fe3 plus was ion. You understand? Don't be confused. Ion. Ion 3 ion. Call it that way. But now we are saying the oxidation number of iodine ion, which is I minus. So to iodine atom. Now iodine atom is now free. It's just I. You understand? The oxidation number increases from minus 1 to 0. What happened? Iodine ion lost that one negative thing that was in its life. It lost one electron. Electron is negative. I'm not saying electron is a bad thing. Take note. Electron is the reason why you have electricity and every other kind of physics, and understand. So, but I'm just relating it to negative things so that you understand better. And if after doing all this you don't understand, God will help you. So, iodine lost that one negative thing. And what happens when you lose electrons? You become more positive. 0 is more positive than minus 1, isn't it? Good. So the oxidation number increased from minus 1 to 0. So you know why it's called increased. Going that way is an increasing it's in an increasing order. So conversely, during reduction, a substance gains electron and its oxidation number decreases in the positive direction. Remember, we said when an element or a substance gains electrons, it's gaining negative things now. What happens? It becomes more negative. So it means to gain negative charges. So let's just look at that Fe that became Fe3 plus. Now, when Fe3 plus is reduced to Fe, we're going back again. Half brother has backslided. He's going back to the world. He's gaining more negative things again. But thank God, he did not become negative. Now, when Fe3 plus is reduced to Fe, Fe3 plus is an ion, Fe is an atom. The oxidation number decreases in the positive direction from plus 3 to 0. You understand how it increased from 0 to plus 3. Coming back the other way, which is reduction, it will decrease from plus 3 to 0. So how did it go? Plus 3, plus 2, plus 1, 0. So you understand why it's in the positive direction. Plus. Okay. When iodine atom that was formed and got repented and lost that negative thing and became neutral is reduced to I minus. Alright, it has gained back its negative charge because it has been reduced. The oxidation number decreases from 0 to minus 1. That will not be our portion in Jesus' name. Okay, so we have some examples there. First one says, what is the change in the oxidation number of iodine ion in the reaction below? Now look at your notes. The first example there, you will see the equation. You see 5I minus plus 6H plus 1O3 minus produces 3I plus 3H2O. Now, since we are asked for iodine ion, we'll pay more attention to iodine. Iodine on the left hand side and iodine on the right hand side. Now on the left hand side we see iodine has one negative charge. We want it to lose that. Actually we can't decide that. You look at the equation should decide what happened. Now looking on the right hand side, iodine is free. It's an atom now, not an ion, but the left hand side is an ion. You understand? Now the oxidation number on the left hand side is 1, -1, so to say, -1, and on the right hand side it is 0, isn't it? It's neutral, it's free, no charge up there. Ignore the 3 now, ignore the 5 on this other side, ignore the 2 down there. Just look at the element. Now in the reaction, the iodine ion loses 1 electron because it just had that 1 negative electron. We remove it. It lost that electron to be oxidized to iodine atom. Always don't forget, loss of electron is oxidation. So since it lost that electron, it means it became oxidized to iodine atom. So its oxidation number it increased from -1 to 0. Okay, the second one says, what is the change in oxidation state of ion in the reaction? Now you're given the reaction 2FeCl3 plus H2S yields 2FeCl2 plus 2HCl plus S. Now I want you to look at the first compound there in the equation. Look at it very clearly. Look at it very clearly and listen. You see 2FeCl3 there, right? Good. Look at the Cl. Chlorine is a halogen, right? Good. And what's the oxidation number of halogens? -1. Good. Now, -1 and the molecule number is 3 down there, right? So Cl3. So if Cl is -1, -1 times 3 gives you what? -3. Good. And remember the sum of oxidation number of a neutral compound. So FeCl3 does not have any charge, so it's a neutral compound. So the sum should be equal to 0. Now, if Cl3 is -3, as we've calculated, that's -1 times 3, then what would Fe be? So that if we add it to -3, the sum should equal 0. If you calculate very well, you see that Fe is +3. You understand? So down there you see the oxidation number of ion in FeCl3 is +3. That's how you calculate it. I'll try and create a video for you to see how I calculate that. So the oxidation number of ion in FeCl2, that's on the other side of the arrow. If you calculate very well, you see Cl is -1. -1 times 2 is what? -2. So everything should be equal to 0. So what will Fe be to neutralize the -2 here? Fe has to be +2. So Fe there is +2. So you see, on the left hand side the oxidation number of ion was +3, but on the right hand side the oxidation number of ion is +2. So therefore its oxidation number increases from +3 to +2. I hope you understand why that is increase. Good. Why it increase? Because you want to get back to get down to neutral, become an atom. Remember, in the positive direction, it should increase +3, +2, +1, 0. It becomes an atom. It's free. So if you follow the same pattern, number 3, number 4, you will see, you understand very well. It's well clearly stated. Just do it step by step and you understand. Okay, so we get to half equations. A half equation shows what happens during oxidation separately from what happens during reduction. Remember we said in the other class that oxidation-reduction reactions are two opposing but complementary reactions. That means oxidation cannot happen without reduction. They happen consecutively. So if oxidation happens soon, reduction will happen and if reduction happens, oxidation happens. So a half equation can help us see what happened during oxidation separately from what happened during reduction. So a half equation shows what happens during oxidation separately from what happens during reduction. Now, when we want to write electrons, we don't spell out electron in equations. We just write small letter E and one minus on top. Not one minus, just minus. E minus, small letter E and minus on top. So that's symbol for electron when writing equations. Now, a half equation is balanced by adding or taking away, same thing as is that you add or subtract, add or take away a number of electrons equal to the total number of charges on the ions in the equation. Now, when positive metal ions, metal like metal or non-metal, now is metal, when positive metal ions, ion of a metal, and positive ions are called cations. When they arrive at the negative electrode, look at it now. It's arriving at a negative point, so it will gain a negative thing. And a negative electrode is a cathode. They gain electrons in that negative thing to become neutral metal atoms. Take for instance, lead is a metal, lead Pb. Now, Pb2 plus under your book is a metal ion, has positive ions there, 2 plus. Now it's moving, it goes to a negative electrode, which is the cathode. It's arriving at a negative place. What will it be gaining? Electrons, which are negative. So when they arrive there, the lead 2 plus will gain electrons to become neutral. How many electrons will it gain? Since it has 2 electrons, 2 positive, 2 cations, yes, it will gain 2 electrons just to become neutral. Now, that is called reduction, because we know that gain of electron is reduction. So in the equation, Pb2 plus gained how many electrons? 2 electrons, because it has 2 positive charges to become neutral lead. So you see how we added equal number of electron. We added 2 electrons, an electron equal to the number of charges. Since it has 2 positive charges, we're adding 2 negative stuff, 2 electrons to balance it up. So that's how you balance half equations. Now, when negative non-metals negative now, metals positive, as we use in this book, anions, arrive at the positive electrode. Look at it now, it's coming to a positive place. It's going to be attracting positive things. They lose those negative stuff, the electrons, to form neutral atoms. All we are pursuing is become neutral, give your life to Christ. Good. So when it becomes neutral atoms or molecules, we'll get to this molecule soon. Now, in the equation, you see Br, bromine, had one negative charge there. Of course, halogen should always be -1, so it has one negative charge there. How many electrons will you add to balance the equation? How many electrons will you take away, since it already has negative? Want it to become neutral, so you're going to take away that negative stuff. So we're going to take away 1 electron. That's why on the other equation, Br plus 1 electron, we take away that 1 electron. Good. Now about the molecule thing, you remember that we said something last time about oxygen gas being diatomic. It doesn't stand as O alone, it's O2. That means it's diatomic. Now, bromine also is diatomic. Chlorine is diatomic. Most of the halogens are diatomic. Now, bromine here was formed only Br, right? Good. When that is formed, it will have to react to form bromine molecule. So bromine will combine with another bromine and become Br2, because it cannot exist as Br alone. So in balancing such equations, we must add that 2 to signify that bromine actually is diatomic. So instead of saying Br minus, we're going to say 2Br minus, so that we're not just taking away one electron. Since there are 2 bromine, 2 negative charges there, it will become 2 electrons we are going to take away on the other side. You understand that? Good. Now go down there and take note. They have equation for oxidation shows electron loss, while the half equation for reduction should show electron gain. So a half reaction or half equation cannot occur by itself. It can only occur together with another complementary half equation. This is because a substance cannot donate. When you say donate, lose, give out. Substance cannot donate or lose electrons, which losing electron, loss of electron is oxidation. So a substance cannot be oxidized unless another substance is present to accept or gain the electrons, which means another substance is reduced. So you see, oxidation cannot happen without reduction, because elements don't just throw away their electrons. Yes, they don't just throw away. It's not that we say it's negative, so lose it, just throw it away. You don't just throw it away. They give it out to another element who is ready to accept. So if there is nothing ready to accept, it remains the way it was. If it was negative, it remains negative. So you can't say oxidation has occurred and there is no reduction, because nothing to take it. Oxidation occurs complementarily with reduction. Do you understand? Good. Okay, so we get into what we might consider the last thing today: balancing redox equations. How do we balance redox equations? Now, the most common way of balancing redox equations is by considering the 2 half equations involved in such reactions. So you will have to consider the half equation for oxidation and consider half equation for reduction. You have your notes with you there, and you've seen the steps for balancing redox reaction. It reads: number 1, you first determine oxidation number. Number 2, figure out what is being oxidized and reduced. Remember our table the other time where we said A and B are sending out electrons, and you remember that the substance that is reduced is the oxidizing agent, and the substance that is oxidized is the reducing agent. So number 2, we're going to figure out what is being oxidized and what is being reduced. Number 3, we'll write our half equations. So since we figured out what is being oxidized, we write half equations for oxidation. Figure out what is being reduced, we write half equation for reduction. Number 4, we'll balance atoms except oxygen and hydrogen. So it's not like we're going to abandon oxygen and hydrogen, but there is a particular way we're going to balance oxygen and hydrogen. So we first balance other atoms apart from oxygen and hydrogen. So if there is no oxygen or hydrogen, if there is no other atom there, okay, we pass and balance and get to the next step. So number 5, add H2O to balance oxygen. So now we're balancing oxygen. You add H2O to each atom of oxygen that you need to balance. You don't add oxygen to the other side and say, okay, so I add oxygen and balance with the other oxygen. No, to any oxygen you see, you're going to balance it using water molecule H2O, and then you will discover that using water molecule you've created H problem. So you balance the H plus, you balance the H using H plus. You will see that when we go on. Number 6, add electrons to balance charges. Remember, not long ago we just did, when you add electrons to positive charges, you end up reducing that. Remember, gain of electron is reduction, so you end up reducing that element to neutral state. If that element was negative already, you are adding you are going to remove electrons, removal of electrons, loss of electrons, which is oxidation. You're going to remove electrons to make it neutral. So you either gain electron, or you either add electrons to make an element neutral, or you remove electrons to make an element neutral. So we're going to do that in step 6, add electrons to balance charges. Step 7, multiply half reactions to make the number of electrons equal on both half reactions. We're going to see that's very easy. Number 8, add the half reactions. So add the reaction from step 7, what you've gotten there on the 2 half reactions, and add them up at the half reactions, and then cancel out the stuff that appears on both sides. Now if the same number appears on both sides, or the same thing appears on both sides, you cancel them out, and what is left is your equation, is your balanced redox equation. Now most times, especially in your WAEC, you are always asked to balance redox reactions. It's not specified if you are to balance in acidic medium or to balance in basic medium. Normally, naturally, when you are not told to balance it whether in acidic or basic medium, automatically it's on acidic medium. So very rarely you will be asked to balance on basic medium. In fact, I've never seen in WAEC. So I just added that from step 9 to 12. After you finish step 8, you have finished your balancing of redox equation for acidic medium. But if you ask for basic medium, that step 8 does not, you don't end there. That's not your last step. You have to continue to step 9, step 10, step 11, step 12. We're not going to do that because we're not going to be asked that in WAEC. But for just the knowledge, when we resume fully, I'm going to take time to teach you that. Okay, so before we start, remember step 1 says determine oxidation number. So before we start, I'd like to throw a recap of what oxidation numbers are for the last time now. Remember, element standing on its own has oxidation number of 0. Group 1 elements always minus or plus 1 oxidation number. Group 2 elements always plus 2 oxidation number. Halogens always minus 1, but when it's bonding with oxygen it's plus 1. Monatomic ion, you know what that means, is equal to its ion charge. Hydrogen has plus 1 with non-metals and minus 1 with metals. Oxygen has minus 2 but minus 1 with peroxides. Fluorine will always have minus 1. Fluorine has always has minus 1, and you know that halogens should have minus 1, but other halogens can change depending on what they are bonding with. But for fluorine, it can never change. It's always minus 1. And the sum of oxidation numbers for a neutral compound, you know what that means, a compound without charge, should be equal to 0. So you use that to calculate. And the sum of oxidation numbers for a polyatomic ion, an ion with more than one atom, is equal to the ion charge. So you have to sum everything up. And the ion charge that is there, if it's in one negative sign on top of the whole compound, then it's minus 1. If it's 3 plus on top of the last compound, which shows a sum of the whole charges, then the oxidation number should be equal to plus 3. You understand? You understand better when we start calculating. So you are given an equation there. You have to balance the redox reaction between zinc and trioxonitrate 5. So you see the equation there, Zn plus NO3 minus yields or produces Zn 2 plus NO2. And step 1 says determine oxidation number. Now the steps are very, very easy. You can see from beginning to the end. It's well clearly written. If you follow suit, you'll be able to understand, but I'll still explain that. But something I want you to get into your memory. Now, if you go down to step 2, we'll come back to step 1 and start solving. I'm planning to put that in a video. But go to step 2, you see, figure out what is being oxidized and reduced. Now, we know oxidation is loss of electrons and reduction is gain of electrons. So, we can use oxidation number to determine oxidize or what is being oxidized. That's the oxidizing agent and the reducing agent. Now, when your oxidation number is going down, that's change in oxidation number. Now, if it was 0 and it's now becoming minus something, oxidation number is going down, right? Good. So when oxidation number is going down, reduction is taking place. Take note, that's not a definition for oxidation and reduction, but I'm giving you a hint. So you see, when you see ON, you see arrow going down. That's when oxidation number is going down, then reduction is taking place. And when oxidation number is going up, you see in that book I wrote ON with an up arrow. So when oxidation number is going up, call that oxidation. So you're going to use that to determine your oxidizing agent and your reducing agent. So I'm going to head on now to create a video. The only fear I have with video is that it will take up a lot of data and might not be able to watch it if you don't have enough data, but I'll try and compress it. So wait for the video. So I've tried as much as possible to record the video in the shortest possible way, but the least I could get was 2 gig for the video, and even when I tried compressing, it came out with something that I can't send. So I don't think I'm going to make any video on that. So, but it would be really good, but we can't do that right now. So I will need you to pay attention and look at that your book. The picture I sent on Sunday. Now I used 2 color of pen. Some I used red pen and the other was the black ink. Now what is on red are the new things written. So the one I'm going to explain, you need to be very, very vigilant in looking at that. So step 1 says determine oxidation number. So look at your book. You said Zn plus NO3 minus yields Zn2 plus NO2. Oxidation number of elements standing alone is 0. So Zn is 0. Plus NO3 minus. It has a minus. So NO3 is a polyatomic ion. It's an ion because it has a charge. Now, so everything should be equal to -1 since the polyatomic charge ion. Its oxidation number should be equal to the ion charge, which is -1. So if you check oxygen there, oxygen is -2. You see an arrow up, -2 there times 3 since it's O3 gives you -6. So if it's oxygen is -6, nitrogen is only left there, and everything should be equal to -1. What -6 will give you -1? If you say 6 minus 6, it gives you 0. But this is a neutral compound, everything should be equal to -1. So 5 minus 6 will give you -1. So oxidation number of nitrogen has to be +5. So you write, I wrote it in red ink now, +5. Now on the other side, zinc is no more standing alone. It has a charge. It's now called a monoatomic ion, and the oxidation number is equal to the ion charge. What the ion charge is 2 plus, so the oxidation number is +2. Now, so oxidation number of zinc on this other side is +2, and now NO2. The last side was NO3. Now NO2. NO2 here, oxygen is -2. Since it's O2, so -2 times 2 gives us -4. And it's a neutral compound, so everything should be equal to 0. Sum of oxidation number for a neutral compound equals 0. So since it's 0, and oxidation number of oxygen is minus 2 times 2, since it's O2, minus 4 here. So what minus 4 will give you 0? It has to be 4. So oxidation number of nitrogen on this other side is plus 4, because 4 minus 4 equals 0. Number 2, we're going to figure out what is being oxidized and what is being reduced. Now remember, we said that we can also use oxidation number to figure out what is being oxidized or reduced. Reduction is gain of electrons, but when oxidation number is going down, we say that is reduction. Reduction has occurred. Oxidation is loss of electron, but when oxidation number is going up, then we say oxidation has occurred. Okay, now we have our equation now well spelled out. So we want to figure out what is being reduced and what is being oxidized. Zinc on this other side, the left hand side, has oxidation number 0, but on the other side it has oxidation number plus 2. What happened to the oxidation number? Oxidation number of zinc increases, so we call that oxidation. So we put an arrow from zinc on this other side down to zinc on the other side, and we say zinc is oxidized because oxidation number increased. Now coming to NO3, we see that nitrogen had oxidation number plus 5 on this side, but on the other side it has oxidation number of plus 4. So what happened to its oxidation number? It was reducing. So oxidation number of nitrogen reduces, so we call that reduction. So we put an arrow on nitrogen on this 5 side, and the arrow continues to nitrogen on the right hand side, so we write the nitrogen is reduced. Now take note, nitrogen and oxygen is a compound, so we will not take out oxygen and leave nitrogen, since we say it's nitrogen that is oxidized. And take note, oxygen is not oxidized, it's not reduced, because it's minus 2 on this side and minus 2 on the other side. Nothing happened to it. So oxygen is not oxidized, it's not reduced. So because of that, you don't say, okay, since nitrogen is oxidized or is reduced, nitrogen is what we need, so you detach nitrogen from oxygen. No, it's a compound, so when you want to deal with nitrogen, you're going to carry it with the oxygen. Good. Now step 3 says write half reactions. Since we've gotten zinc is oxidized, nitrogen is reduced, we can use that arrow, that's our arrow that we wrote, zinc is oxidized, and that arrow that says nitrogen is reduced. We can use that arrow to form our half reactions. Now for oxidation, we would say Zn, follow the arrow from Zn. Zn, the arrow is on the other, the arrow ends on the other side of the equation, so we put an arrow. Zn produces, where the other one stops now, Zn2+. Please try and follow, because this is not a video. On the reduction side, remember you don't take only N out, so NO3 on this side, follow the arrow. Oh, it crosses the arrow sign, so you put an arrow, ends at NO2, so you write NO3 minus yields NO2. I hope you understand that. Just check that very clearly and you will understand. Okay, so step 4 says balance atoms apart from oxygen and hydrogen. Now you see that in the reduction equation you have oxygen, so you will need that balancing of equation. Let's take out reduction and start there. You will know why, because oxidation is not as tedious as reduction, because I only want one atom. Yes, so let's take out reduction. For reduction, NO3 minus yields NO2. On the left hand side we have nitrogen 1, and on the right hand side nitrogen is 1. On the left hand side we have oxygen 3, but on the right hand side we have oxygen 2. But we're not to balance oxygen yet, so we balance nitrogen. It's already balanced, so we don't have anything to do there. Now we get to step 5, which is to balance the oxygen. Now add H2O to balance oxygen. That means to every one oxygen you need, you will add 1 molecule of water, 1 H2O. So you don't say since you need oxygen, you just add plus oxygen. No. To add oxygen, you have to add water. Water has oxygen in it. Good. So if you check on the right hand side, we have 2 oxygen atoms, but on the left hand side 3. So we need 1 oxygen atom on the right hand side. So since we need 1 oxygen atom, we have to add 1 molecule of water. You understand? So you see in the question in step 5, I now wrote plus, on the right hand side, plus H2O. Now if you now count the number of oxygen atoms on the right hand side, you see is O2 is 2 here, plus the other O in H2O, which is 3 oxygen atoms now. So it's no more 2, it's 3. So oxygen looks balanced. But we have created a hydrogen problem for this whole equation. We've introduced hydrogen into the equation, so we have to put it in our account. H equals to 2 on the right hand side, but it's 0 on the left hand side. So step 5 said balance H2O, add H2O to balance oxygen. Now and H plus to balance hydrogen. Now you're not going to just add H to balance up with the hydrogen here. You're going to add H plus as an ion. So how many hydrogens do we need? We need 2 hydrogens. So we're going to add 2H plus. So that's why I added on the other side 2H plus, and hydrogen is balanced. So if you now count, our atoms are balanced. Nitrogen 1, oxygen 3, hydrogen 2 on the left hand side. On the right hand side, nitrogen 1, oxygen 3, hydrogen 2, atoms balanced. So we move to step 6. Step 6 says add electrons to balance charges. Now step 5 is to balance atoms, step 6 to balance charges. So you balance atoms and then balance charges. Now in balancing charges, still take note, the red pen is the result, what I put after I have finished calculating. So we are going to deal with that equation without the stuff I wrote on red pen. So if you did not differentiate the colors as I wrote, you have to go back to the original photo I sent on the group and look at it so that you know which one is in red or which one is in black or blue pen. So check well. Now if you look at that equation, it is 2H plus, that's equation 5, step 5 equation is 2H plus NO3 minus yields NO2 plus H2O. That's the equation I started with in step 6. So when you start with that, if you check the electrons or the charges on the left hand side, you see 2H plus has how many electrons? H has one positive charge there. So but the mole number is 2. Remember, mole, the big number, affects the charge. So it's not one positive charge, it's 2 positive charges. But if it was molecule number, like you have NO3, the O3, the small 3 there, the small numbers don't affect the charge. So you cannot say this is 3 minus, no. But if there was a 2 in front of N, that would affect the minus in NO3. So it shouldn't affect since there's nothing there. So now on the left hand side we have 2 positive charges. So we write it out. If you check in step 6 now, I wrote now plus, since it's 2 positive charges. Now if we move to NO3, you have only 1 negative charge there, which means minus 1, right? So I wrote plus 2 minus 1. If you add that up, plus 2 minus 1 is what? Plus 1. So we have plus 1. Now stop there, go to the other side of the equation. You see there is no charge, so everything is 0. It's already neutral. Now we want to balance charges. Balancing charges means let's bring everything down to neutral, just like the other one is. So 0 on the other side, we have to make this side 0. Remember, our answer here is plus 1. So if you have one positive, if an element has one positive charge, we need to add one negative charge to it for it to release that positive and become neutral. So since it has one positive, we need one negative. So we had one electron. Remember, electron is negative, so that's why in the equation I added E minus plus 2H2. That E minus means I've added one electron. If it was more than one, I would write 2 E minus. So E minus. Now since I've added the E minus, that's 1 minus 1, and now bring it to my calculations down there. So it becomes, since the answer was plus 1, I add minus 1 since I've added the 1 electron, and everything becomes 0 on the left hand side. So 0 on the left hand side, now 0 on the right hand side. Now you've balanced the atoms and ions for the reduction half equation. You repeat the same thing for oxidation. Now, but if you look at oxidation, oxidation has equal number of atoms on both sides, so we don't have to balance atoms other than oxygen and hydrogen. And now it doesn't even have oxygen, so we don't have to spend time adding water molecule and then creating H problem and adding H plus to balance that. So that's why I said let's take reduction first. So oxidation is quite simple. So atoms are already balanced, so we go straight to balance charges. Now on the left hand side we have Zn, 0 charge, low charge. But on the right hand side we have Zn2 plus, which means the charge is plus 2. So what do we add there? We need 2 negative things to remove that 2 positive things. So we add, electron is negative, so we add 2 electrons. You see that plus 2e minus. And since you've added 2e minus means minus 2. So I brought in the minus 2 to the equation, plus 2 minus 2, which becomes 0. So the charges are neutral now. Left hand side 0, right hand side 0. So your atoms are balanced on the oxidation reaction. The charges are now balanced. We move to step 7. Step 7 says multiply half reactions to make the number of electrons equal in both reactions. Now if you look closely, you see that the oxidation half reaction is Zn yields Zn2 plus 2e minus. It has 2 electrons. But the reduction half equation is E minus plus 2H plus NO3 minus yields NO2 plus H2O. It has only 1 electron, E minus, whereas oxidation has 2 E minus. If we allow this thing to be like this, it means that on the reduction side, since it has only 1 electron, it means 1 electron was gained. But on the oxidation side, 2 electrons was lost, or 2 electrons were lost. We cannot say electron loss is not equal, or according to this equation, electron lost is not equal to the electron gain, but it's supposed to be equal. So we want to make the electron loss equal to electron gain. So how do we do that? Since oxidation half reaction, we can call that equation 1. Since it has 2 electrons and reduction has 1 electron, we multiply the one that has 2 electrons by 1 and multiply the one that has 1 electron by 2. You understand? We're just trying to create a balance between 2 of them. Now if you go down, you see how I did that. Oxidation, since Zn yields Zn2 plus 2e minus is just times 1, it's going to remain that same way. But the reduction, since all of them is multiplied by 2, the reaction is going to look like or everything times 2. So E minus becomes 2E minus, 2H plus becomes 4H plus, NO3 times 2 becomes 2NO3 minus, yields NO2 was 1, so times 2 it becomes 2NO2 plus H2O was 1, so it becomes 2H2O. Please understand that clearly. So if you look at the new equations we've brought out, you discover that now oxidation has 2 electrons at the end, reduction has 2 electrons at the beginning. So they are now balanced. It now means electron gained on the reduction side is equal to the electron lost on the oxidation side. So we have achieved step 7. We move to step 8. Step 8 says add the half reactions, cancelling out stuff that appears on both sides. Now when you're adding the oxidation and reduction half reactions, if you look at that my equation, Zn arrow Zn2 plus 2e minus, I should have kept that arrow, the arrow of the oxidation, to stay in a straight line with the arrow of reduction, so that by the time I want to add, I will know that everything on my left hand side for both equations are just on the left hand side, and the arrow on the straight line aligning with one another separates them from the elements or the equations in the right hand side of both equations. So you can write it out so that the arrow is at the center of the two of them are together. So we want to add everything on the left hand side, both oxidation and reduction together, everything on the left hand side, until where we see arrows on both of them. Then we put our arrow and then add everything that is on the right hand side of both the equations. So let's go. It's going to be Zn, and now remember, since it's addition, it's not a must that it should be Zn before 2e minus before 4h plus, because since it's addition, 1 plus 2 plus 3 plus 4 will give you the same answer as 4 plus 3 plus 2 plus 1. All right, good. So we're going to add everything on the left hand side of both equations, put an arrow, add everything on the right hand side of both equations. Let's go. Left hand side, zinc Zn plus 2e minus plus 4h plus 2NO3. Now we've met the arrows for both of them. Move to the other side of the equation. Yields, we'll put our arrow, Zn2 plus 2e minus, go to the other side, the next equation, 2NO2 plus 2H2O. So we now have a straight line equation. Now we're going to cancel out stuff that appear on both sides. If you look at the equation, nothing else apart from 2e minus appear on both sides. So we cancel 2e minus out, and we are left with our equation. Zn plus 4h plus 2NO3 minus yields produces Zn2 plus 2NO2 plus 2H2O. Now that's our balanced redox equation in acidic medium. Actually, that's what you're going to be asked. It may not be pronounced in acidic medium, but that's a balanced redox reaction. Now if you were asked to balance in basic solution, that's when you would follow the next steps and continue. That step 1 will become step 9, you understand. But since you're not going to be asked that, let's not spend time doing that now. But when we resume fully, I might go through it one more. But if you can go through it alone and you will understand. Please, I need your utmost focus on doing this. Since it's audio and not video, go through it again, listen to this audio, store it. You can keep it by your side and listen to it over and over again until you are very clear, you understand very well. All right.